Okay, so let's continue this discussion on the transgression of the planetary boundaries. Let's go back and read the definition of novel entities which has been added here. We already said that is chemicals. Oops, sorry. The definition of this boundary is now restricted to truly novel anthropogenic introductions to Earth system. These include synthetic chemicals and substances, for example, microplastics, endocrine disruptors, and organic pollutants, anthropogenically mobilized radioactive materials including nuclear waste and nuclear weapons, and human modifications of evolution, genetically modified organisms, and other direct human interventions in in evolutionary processes. Novel entities serve as geologic markers of the Anthropocene. The word Anthropocene is still being used, even though the official geologists' body said this cannot be an official geologic period yet. However, their impacts on Earth's system as a whole remain largely unstudied. For example, microplastics, nanoplastics, plastic pollution in general is studied extensively, and nanoplastics are found in human blood, maybe brain, breast milk, and so on, but the actual impacts on health are not as well quantified as just the prevalence or presence of these pollutants in human body. Okay, so this is to be studied further. The planetary boundaries framework is only concerned with the stability and resilience of Earth system, i.e. not human or ecosystem health. Thus, it remains a scientific challenge to assess how much loading of novel entities Earth system tolerates before irreversibly shifting into a potentially less habitable state. Okay, so it's good to know their definition. Again, lots of subjectivity is included there. Let's look at the impact of the combined effect of land system change and climate change boundary states on trajectories of terrestrial carbon stocks and global land temperatures. So here you have land carbon sink, so long-term cumulative, and land carbon source, again long-term cumulative. And if you start in 1998 as a baseline, you go back here in terms of 100 gigaton of carbon as a scale, so 50, 100, 150, 200, and again 50, 100, 200, and so on. And here you're looking at climate change, so in terms of planetary boundaries, so you have atmospheric CO2 concentration scenario fixed as opposed to 350, 450, and 550 ppm. Land system change planetary boundary in terms of percentage of boreal temperature, tropical forest remaining, for estimating the carbon sinks and sources. On planetary boundary 85, 50, 85, so that's you are staying on the boundary with certain probabilities, and on upper end of the zone of increasing risk, so 60, 30, 60%, beyond the zone of increasing risk, and short term. So this is long term, medium term, short term is open circle, long term, and so on here. Okay, so you can try to match, but basically it's a projection, so you have to be always careful because lots of uncertainties in these things. Results are based on idealized Earth system model experiments with varying planetary boundary status, ranging from maintaining the planetary boundary at 85%, 50% to 85% for boreal, temperate, and tropical forest remaining. So that's what I meant here as well. And 350 ppm atmospheric CO2, so you are in this zone here. The upper end of the zone increasing risk for 60%, 30%, 60% for 450 ppm and orange. So lots of complicated terminologies, and beyond the zone of increasing risk, but you get the idea. The colors denote the state of the land system change boundary, while the climate change boundary is shown on the y-axis here. The locations of the circles on the x-axis represent the changes in the land carbon sink, so you are looking at those here. Baseline plus 3.38 degrees C warming, plus 0.6 degrees C warming for long term, short term, and out to 2770, 2100 here. So I'm not sure I want to go into the details here. Okay, so it's just a way of depicting how land use change, land carbon sink and source will respond based on the assumptions of how much tropical boreal and temperate forest covers remain, and so on and so forth. So global average change in 3 scenarios from the initial state 1988 to 2018 baseline: change in sea surface temperature delta SST, new production delta NP, and biogenic particulate flux below 500 meter depth. So that's export of carbon, including model and empirically derived values. Surface saturation state of aragonite, which shows you loss of carbonate ion, and the dissolved inorganic carbon inventory between surface and 1000 meters, which also corresponds to let's say the sink of the ocean, as well as carbonate ion balance and so on. So with increasing CO2 concentration, you expect the warming to increase, and net primary production change to be drop to zero and go negative, so you will lose ability to photosynthesize and net primary production. And this is the empirical percentage delta. The carbon flux also drops off, so if production drops, you expect flux to drop off. Aragonite saturation goes negative, and delta DIC also increases, basically in terms of delta increases, so gigaton of carbon. So dissolved inorganic carbon is increasing. You can do what you want with it, but basically you get the idea that they are extending the planetary boundaries idea further. And here let's read the words in which they explain a systemic framework for addressing global anthropogenic impacts on Earth system. The scientific updates and analysis presented here confirm that humanity is today replacing unprecedented pressure on the Earth system. Perhaps most worrying in terms of maintaining Earth system in a Holocene-like interglacial state is that all the biosphere related planetary boundary processes providing the resilience, in other words capacity to dampen the disturbance of Earth system, are at or close to a high risk level of transgression. So we'll tip over beyond the safe operating space in this sense of planetary boundaries. In a recent study, it was shown that several regional climate tipping points relevant for stabilizing the global system have already been or are close to being transgressed, thus weakening global resilience capacity. These are a lot of words, and there is a lot of disagreement on this whole tipping point business, because they are heuristic empirical arguments, and if you are saying some things have already been crossed, then again, what are the impacts? And when we say we are really closer than we think, you're taking models that don't really predict tipping points, but you are trying to derive based on indicators or early warnings of tipping points, saying we are really close. So not everybody agrees with this kind of an approach. It's very popular in Europe, but not so popular elsewhere. This implies low falling resilience precisely when planetary resilience is needed more than ever to cope with increasing anthropogenic disturbances. Measuring resilience itself is tricky, but it's clear that we are making huge impacts on the warming, greenhouse gases, glaciers, sea level rise, health, crop yields, many things. So obviously some sort of weakening of the resilience is happening, mostly as applied to us. The planet is not going anywhere, biology is not going anywhere. Some species will pay a price, and that could be us as well, right? There is an urgent need for more powerful scientific and policy tools for analyzing the whole of the integrated Earth system with reliability and regularity, and guiding political processes to prevent altering the state of the Earth system beyond levels of tolerable for societies today. In addition to more consistent collection and collation of relevant global environmental data, this will require the development of Earth system models that more completely capture geosphere, biosphere, anthroposphere interaction than is the case today. This is a tall order just in terms of capturing all of the biosphere by itself, geosphere, and the anthroposphere and their interactions and feedback. The known interdependence of planetary boundaries is confirmed by the Earth system science understanding of the planet as an integrated, partially self-regulating system. To better understand the risk to this system and the critical boundaries that humankind should consider in its economic and social activities, Earth system analysis now has to continue advancing a planetary boundaries framework. So we have adaptation, mitigation, which are already struggling in terms of climate action. A lot of geopolitical perturbations or COVID and so on tend to put everything back on the back burner. Now we are adding another requirement of planetary boundaries framework, and it needs new data, new models, and of course new agreements, let's say. In addition, it must substantially increase the ecological realism of simulation and analysis of the biosphere as an adaptive core entity of Earth system. These initiatives are underway but have to be further developed into a coherent process of integrated Earth system analysis across the physical, chemical, and biological domains, not focused just on climate. Successfully addressing anthropogenic climate change will require consideration of internal biosphere-geosphere interactions within the Earth system. Our model results demonstrate that one of the most powerful means that humanity has at its disposal to combat climate change is respecting the land system change boundary. That's why they looked at that figure of how carbon sink and source on land will change with warming. Bringing total global forest cover back to the levels of late 20th century would provide a substantial cumulative sink for atmospheric CO2 in 2100, remembering that wildfires can burn up all that carbon and release it in a second. This reforestation seems unlikely, however, given the current focus on biomass as a replacement for fossil fuels and the creation of negative CO2 emissions via bioenergy with carbon capture and storage. Both activities are already serving to increase pressure on Earth's remaining forest area. Nevertheless, our study indicates that failure to respect the land system change planetary boundary can potentially jeopardize efforts to achieve the global climate goals adopted in the Paris Agreement. Lots of words, lots of assumptions involved in these things as to what roles forests will play and so on. And again, the forest is not silver bullet. Afforestation or increasing forest cover has lots of other barriers and so on. Meanwhile, this update of the planetary boundaries framework may serve as a renewed wake-up call to humankind that Earth is in danger of leaving its Holocene-like state. It may also contribute to guiding the substantial human opportunities for sustainable development on our planet. So there are a lot of no-regret decisions. We can have sustainable development, better standards of living, and yet be kinder to the planet. Scientific insight into planetary boundaries does not limit but stimulates humankind to innovation toward a future in which Earth system stability is fundamentally preserved and safeguarded. Obviously, this is a very nice and holistic and optimistic view, and you would want sustainable development, you would want reduced emissions, net zero, and so on. The question is how planetary boundaries will complement the other approaches of directly decarbonizing the system, lots of sustainability done sectorally for food, water, energy, health, transportation, buildings, and so on, agriculture, and adaptation for dealing with things that are already happening and will continue to happen till we peak our emissions and then begin to turn down the emissions and wait to see how much the committed warming will what the committed warming will do in terms of the warming and what their local impacts will mean. So all these are difficult issues. So whether integrated planetary boundary approach adds new dimension to doing things is not clear, but that just shows that I'm a little bit skeptical about this. So you can read up and follow up and decide for yourself whether this really adds value to just driving mitigation and adaptation.